All right, so we got another 2.5 minutes or so. Oh, here's Tom typing something. Yeah, I decided to turn it monochrome, because it's really hard. Most webcams are not nearly this hard, but I think this one, I probably have to check the specification, when I order this camera, because I think it's still sensing infrared, so the color balance is always off. Okay, so it's just a little bit hard. So I just decided, hey, why mess with the color when there's no need to use any color, right? I mean, so yep. So monochrome from here on. Yeah, so I haven't even started on lower decks yet, because there are also a lot of other shows to watch on both Amazon and Netflix. So I haven't started on this one yet. Eddie Murphy. Okay. Well, color is an interesting sensation, because humans are actually one of few animals that has color vision, because we have receptors for several different frequencies, and by mixing the signals from those sensors, we have the perception of colors. And not too many animals actually have the sensation of colors, like cats and dogs don't. All right, let me just check the time. We got about another 30 seconds. So just a quick overview of what we are going to talk about today. And the recorder should be started already on YouTube side. So, so everything is being recorded already. So what we'll do today is we're going to finish the number addition, binary number addition module today. And even though we only have a little bit left from last time, that a little bit left is actually interesting because it takes quite a bit of explanation for that portion. So when we're done with the binary number addition module, we might have time, so that I can actually implement a carry ripple adder in LogicSim so that you guys can see how that works. Okay. But your lab, which is later on, okay, you can see on my screen right here, it is not available to you yet. But your assignment is to implement a carry look ahead adder, not a carry ripple adder. So it's really important because every single semester someone is going to copy the carry ripple adder and turn it in as a carry look ahead adder. Okay, so I hope this year nobody is going to make the same mistake. All right, so it is time to get started. So I'm gonna go to the module and skip all the way to, but wait, there's more. So here it is, okay, but wait, there's more. So the idea of a carry ripple adder is K3 depends on K2, K2 depends on K1, and K1 depends on K0. So that is kind of an issue because until we have K1 calculated, we cannot compute K2. Until we have K2 calculated, we cannot have K3 and so on. Now, it's not an issue if we don't need the carry to compute the sum, but we do. So the K bits are needed in order to combine with the Q bits to get to the sum, the S bits. Okay, so all of these notations we talked about in the previous class on Tuesday. So I'm not going to go through that portion to kind of remind you guys what is the S term and so on. Okay. So what we want to do at this point is to see if there's a way so that we don't need this linear dependency. The linear dependency means if you have an adder that is that takes up n bits, then the time to finish the calculation, to finish the addition, is proportional to n. So if you double the number of bits to add, then you have to double the amount of time in order for the adder to have all the bits computed. So this is not good because when we double the width of adders in processors, because now we are up to 64 bits. Every time we double, we have to also double the amount of time, which doesn't work very well. Okay, when we want the computers to be, or when we want the computers to compute as quickly as possible. So what we're doing today is to see how we can break that dependency. So what we do, over here is we start with the definition that we already know. Ki plus 1 depends on, or is, the actual, this is not a sum, this plus is a logical OR. So it is the logical OR of the carry bit of adding xi, yi, and also the carry bit of adding qi, ki. So all of these terms were introduced in previous classes, maybe just the previous class, but they were already introduced. So I'm not going to spend too much time to go back and redefine the terms. Now, in the lecture on Tuesday, we also mentioned how computing the carry bits in base 2 is really nice because we can replace that with conjunction. So xi, yi may look like multiplication, but it's not. Okay, it is actually conjunction. So xi and yi, this is qi and ki, and then the disjunction, which is the OR, is the last operation. So we have the conjunctions done first, and then we have a disjunction on top of the results of the conjunction. So from the first line to the second line is really just the definition, how we define the carry function for binary numbers. And then from the second row to the third row has to do with how we define the q bits. So qi is really just defined as the single digit result of adding xi and yi. Okay, so up to the third row, everything is really just by definition. Okay, things that we have seen already. From the third row to the fourth row is also something that we have talked about on Tuesday. So even though the R function of xi, yi can be done using exclusive OR, it can be done as xi exclusive OR yi. But if we don't want to use exclusive OR because it is not an operator that we have been introduced to in CISP310, we can replace it with something that looks a little bit kind of complicated, which is xi and not yi, or not xi and yi. So we talked about this also on Tuesday. So up to the fourth row are things that we have already talked about. So from the fourth row to the fifth row, now that is new. Okay, that's Boolean algebra, which doesn't look very different compared to normal algebra, because this is really just distribution. Okay, so when you have a plus b in parentheses times c, then you can distribute it and it becomes ac plus bc, right? So in Boolean algebra, as it turns out, that works too. So I'm just distributing ki to the individual terms of the disjunction, and then the overall become a disjunction as well. And just like in normal algebra, disjunction, just like addition, is associative. So that means parentheses, I don't need extra parentheses to indicate the ordering of performing disjunctions. All right, moving on. At some point, I'm going to lose track of which row we are talking about, so I'm just going to point to it unless somebody has an accessibility requirement, and then I will try to do some more counting in that case. So from this row to this row here, we're introducing this extra 1, which you can also do in normal algebra, right? Because in normal algebra, anything times 1 is the original thing. But in Boolean algebra, anything and true is also the original thing. So let me just say that one more time, because it doesn't, okay, what did I just say? Okay, this is the virtual whiteboard. So what I just said was anything, which is x, you cannot see it just yet here, but I'm gonna show you what I mean by that. Okay, there we go. So anything and true is just the original anything. Okay, and this is not in normal algebra, this is Boolean algebra. Okay, so the x is a Boolean variable, and then the 1 is representing true. So how can we, I mean, In normal algebra, we look at something like this and we say, okay, it's an axiom, okay? And we don't ask why the axiom is the way it is. We don't ask for proofs of the axiom. But in Boolean algebra, we can actually do that, okay? So the way we prove this one is to create a truth table. So the truth table is going to have x in it, and it's going to have x and true, okay? You cannot see it just yet, because I'm still working on it. Okay, you can see a little bit of it, but not the entire thing yet, because I'm going to format this as a table. I'm using Markdown, syntax to create a table, which is really kind of handy because, it can create tables, pretty easily. So x is an independent variable. I mean, it's the only variable. It has to be independent, right? Because there's nothing for it to be dependent on. So x can be false. It can also be true. When x is false, what is false and true? Okay, I know the picture doesn't show a table just yet, but I just want you guys to kind of focus on what I'm asking. What is false and true? False and true is false. Okay, very good. And when x is true, what is true and true? It is just true itself. Okay, very good. All right, so now we have the entire truth table. So when you look at this truth table and you look at the column of x, okay, it has the values of 0 and 1, and then you look at the column of x and true, it also has identical values for every single row. So this is a very cool way to prove things in Boolean algebra, because this table shows us once and for all that x is the same as x and true. Whatever x is, okay, as long as it is a Boolean value, it is the same as whatever x is and true. Okay, so getting back to the notes. Okay, so that means I can introduce and true anytime I feel like it. Okay, so on this particular row, I just felt like it. Okay, instead of just saying xi and yi as a conjunction, now I want to say, well, I will call this xi and yi and true, but because of the axiom that we just talked about, it is okay. Okay, we don't have a problem with that. And then on the next row, okay, the true gets a little bit more complicated. The true becomes true or ki. Okay, so once again, we want to see, well, but can we prove this particular, way of thinking? Okay, if I just start to introduce a Boolean variable ki in this case, is true really the same thing as true or whatever that new Boolean variable is? Okay, so Daniel can see it, but can we prove this using a truth table? That's the other question. So to prove this using the truth table, we'll do something just kind of like before. So this time is actually easier. Okay, we still have x as a variable, but this time we have true or x. Okay, so let's go ahead and check out how the columns will turn out to be. So there you go. Okay, these are the heading. So x can be false and x can also be true. Okay, so I just need to go in and fill in the question marks. When x is false, what is true or false? Well, true or whatever is true. Very good. Okay, so we all got it. So on the next row, okay, let me show the answer here. And it's not showing. There you go. Okay, so on the second row, when x is true, then we're asking what is true or true, and that's even a more stupid question, right? It is a stupider question, and because it is just true. Woohoo! Okay. So now we need a third column, okay? Because we are not really comparing x versus true or x. We're comparing true or x versus true itself. Okay, so now we need a third column, and now we have the table, and now we say, hey, true is always true regardless of the variable x, so we put a 1 here. True is always true regardless of x, and we put another 1 over here. So this is the truth table that we are going to use to show that true versus true or whatever Boolean variable they are really the same thing, because you can see how this column, the middle column, have both rows being true, and then the last column, or the rightmost column, also has true for both rows. So this is basically a proof. Okay, this is a very easy proof in Boolean algebra to show that yes, I can start to introduce additional things in using OR when one of the things is true already. Okay, so now from this row to this row, I use distribution. So this one goes along with this one, and then this ki goes with this one over here. And then on the next row, I do something that you cannot do in normal algebra. Okay, because in normal algebra, you cannot just say, I'm going to take one of the components in a addition, and then I'll just have one more of that thing in the same addition. But in Boolean algebra, we can do that, right? So look at this one here, xi and yi and ki. It is here, but it also has an extra copy over here now. Okay, but we can do that in Boolean algebra. You cannot do it in normal algebra, but we can do it in Boolean algebra. So I'm not going to show you why it works or how it works. For those of you who want to know how it works, you can look at this as an ungraded assignment, okay, and use a truth table to prove that. Okay, it's not going to be a very complicated truth table, given that we already have two done already. You can probably see how you can adapt those two to show this. Okay, so from this row onto this row here, I put in extra parentheses, so I group these two terms into its own disjunction, and I group these two into its own disjunction. So technically speaking, this is using the associative law of Boolean algebra, okay? Because I can put parentheses any way I want, okay? As long as we are just talking about something or something or something or something, okay? So I can perform the OR operations in any order I want. Because of the associative property. Now, how do you prove the associative property? A truth table, okay? So truth tables are actually very, very, very helpful when it comes to Boolean algebra, because it is a very visual way to look at how axioms work, okay? And it's pretty conclusive too. There's no philosophical question of, why does that work? Well, the table shows that it works. Okay. So from here to here, we are doing exactly the opposite of distribution. So you can call it the inverse of distribution, which is otherwise known as factoring. So we can see that xi and ki are common terms within these two conjunctions. So we extract xi and ki out, and then whatever is left, one has yi, the other one has not yi. Then I use another term, with a conjunction to express those two that are different, okay? The subterm in the conjunction that are different. You can do the same thing in normal algebra, we call it factoring. And then we also perform factoring on these two terms, except, in this case, yi and ki are the common subterm within the two conjunctions, and then the one single term that is different between the two, one has xi and the other one has not xi, so those two were basically factored out into its own expression. And then from here to here, we did a simplification, because we see we have yi, and this is OR, this is not yi. So when you have an expression where you have an expression and then you OR the negation of the same expression, then you always get true, because between these two, okay, one of them has to be true and the other one has to be false, okay? And because one of them has to be true, using a disjunction, if at least one side is true, the entire thing is true, and that's why it is guaranteed to be true here. And then the same applies here, because we have xi or not xi, so that means at least exactly one of these terms is going to be true, and as a result, the disjunction is guaranteed to be true. So we now simplified out the true here, because we know that anything and true is just the anything. So from here to here, we just get rid of the extra one because it's not needed. And then we perform one more step of factoring, because when we look at xi and ki, and then we look at yi and ki, and there's an OR in between, So we can see that ki is a common term, so we use factoring to factor out the ki, so it's outside. And then the term that is different within the two conjunctions, one has xi and the other one has yi, so those two terms become its own disjunction, and then the disjunction is ended with the common term that we extracted out of the two conjunctions. So we ended up with this thing over here. So anyone who has been paying attention since the beginning of the lecture will look at this and go like, but Tech, this is not answering your earlier question. It's not addressing the issue that ki plus 1 depends on ki. Because when you look at the beginning, we have ki plus 1, and then you look at the end, we still have, ki as a part of its definition. Now we got rid of the really ugly, exclusive OR thing, and now it's just boiling down to the conjunction of xiyi and the disjunction of xiyi, but we have not gotten rid of ki. Okay, so now the question is, what is the big deal of this entire derivation? Well, the big deal of this entire derivation is we are preparing the expression of ki plus 1 in a way so that we can make a term for xiyi, we can make a different term for xi or yi. So if you have your own browser up, and you're reading a little bit ahead of me, this paragraph may look kind of innocent, but I will tell you that in most semesters, people miss this paragraph all the time. Okay, this paragraph turns out to be really important, because this is where we define a G term. Gi is defined to be xi and yi. Pi is defined as xi or yi. So this is the only place that G and P are defined. And yet it doesn't look like it's really important, but it really is important. So if you have printed out the notes, okay, I would suggest using a highlighter, just to highlight these two definitions. If you're looking at this online, okay, there are other tools that you can use to highlight, in a PDF or something else. Or you can just kind of rewrite these definitions into your own notes, okay? You can take a screenshot, just extract that portion and put it into yours. So Tom has a comment here. He says, so the xi and yi becomes g of I, and then xi or yi becomes p of I. That is correct, okay? These two are definitions, so don't ask me at this point why that is the case. I'm simply saying, oh, I'm getting tired of saying xi and yi. We'll just call that g of I. I'm tired of saying xi or yi. I'm just going to call that p of I. Okay, so those are just definitions. Okay, there's no particular reason to explain why that is the case, at least not now. Okay. So now that we have defined what is gi and what is pi, and then we look at this original expression, then we go like, okay, it's not a big, huge jump, but we can simplify, ki plus 1 now to be expressed as gi, because gi is xi and yi, or pi ki, because pi is xi or yi. That's how pi is defined. So now we can re-express ki plus 1 as a slightly different expression. It still depends on ki, but it is a little bit less clumsy. It is a little bit more, it's a little bit cleaner. It has a particular format to it. So are we okay so far? Does everybody follow up to this point that we can define ki plus 1 as gi or pi and ki? Gi being defined as xi and yi, pi being defined as xi or yi. So are we okay up to this point? Because we haven't really quite get to the magical part. We're just polishing the magic wand at this point. Okay, cool. So here's the fun part, okay? This is the fun part. So the fun part, I'm gonna show it step by step, okay? So I'm gonna apply this kind of general template, except I'm gonna say, let's see what happens when I equals to 0, okay? So we substitute I as 0. So g of I becomes g of 0, p of I becomes p of 0, k of I becomes k of 0, and then k of I plus 1 becomes k of 0 plus 1, which is k of 1. So this is not very surprising, is it? Okay, because all we did is to say, let's see what happens when I equals to 0. Okay, no big deal. Okay, so now we ask another question, okay, which you probably have guessed already. What happens when I equals to 2? Okay, we just step it up by 1, and then we'll try to find out what happens when I equals to 2. Excuse me, when I equals to 1. So now if I do that, then I have, okay, unfortunately it steps to a little bit too much. Okay, let me see if I can scroll a little bit less. No, it's stepping way too much. All right, that's fine. We'll do it that way then. Okay, fine. Okay, so if we say what happens when I, when this I over here equals to 1, okay, not too exciting. Then we have G1 because I equals to 1, G1 or P1, K1. And that becomes the expression that will give us K2, because remember, I is 1, 1 plus 1 is 2, so that's why this term or this expression is telling us what K2 is. But when you look at this K1 here, then we go like, hey, didn't we know what K1 already is from the previous step right here, right? So instead of referring to this as K1, we say, how about we expand it, right? We expand K1 to the expression that we have already worked out for K1. Okay? It's not exponential, it's actually just linear. So now we can see how we can re-express K2 to become G1 or P1, and then in parentheses G0 or P0 K0. Okay, G0 or P0 K0 is just from the step that we have done earlier, because we know that K1 is G0 or P0 K0. So instead of using K1, I'm using G0 or P0 K0. And then we look at this and go like, yeah, it is okay, but it looks kind of clumsy because we have we like things to be a little bit more structured, and this is not very structured. So we use distribution. So once we apply distribution, then we have P1 G0 as its own conjunctive term, and then we have P1 P0 K0 as its own conjunctive term. So now we can define K2 without using K1. This is the magical step, okay? This is the magical step of getting rid of K1 when we want to compute K2. We started off using K1, but because we know how K1 boils down to G, P, and K0 terms, then we can do the distribution, and then we end up with an expression that does not make use of K1 when we want to compute the value of K2. So is this okay? Does everybody understand how we got to compute K2, but without using K1 anymore? So when you see me looking at the side like this, I'm looking at the text channel to see if there are any questions. It doesn't look like there are any questions. All right. Or are you guys still thinking? If you need some more time, that's okay. You can just type on the text channel just a few moments. All good? Okay. All right. So we're gonna move on. So once again, you can always just kind of let me know that you need more time. So now we want to look at the case when I equals to 2. Okay, so we are using the same general template equation here, except we are using I equals 2. So that means we're dealing with G2 or P2 K2, and then the expression is going to give us the value of K2 plus 1, which is K3. So we look at that. Okay, slide down a little bit. Okay. So now we have K3 equal to G2 or P2 K2, and that's just coming from the template, which is no longer in view, but you guys already remember that one, right? And then we look at this and go like, hey, don't we know what K2 is? Yep, we do. Okay, in the previous step, we just expressed K2 without using K1. So K2 itself is this kind of long-ish, messy-ish expression, but that's okay. We just say, Okay, we'll expand K2 to the expression that defines it. Okay, and then we use distribution again. So now we can re-express K3 as a kind of bigger disjunction of G2 as one term of the disjunction, P2 and G1 as another term, P2, P1, G0 as another term, and then P2, P1, P0, K0 as the last term. Okay, but you can see how we can now express K3 only referring to K0 and the P and the G terms, and and a little bit of conjunctions and disjunctions. So are we good up to K3? Are we good? So using this method, obviously we can do everything. Okay, thank you for all the confirmation. So using this method, we can now work on, say, K4, and then after K4, we can work on K5 and so on. But if I were to ask you, which is something that Intel engineers probably have to answer, and say, what do you think K64 would look like? Are you going to do this all by hand and go like, okay, let me do K4 and then K5 and then K6, and then before you know it, you need a lot of pieces of paper. Exactly. This is what computer science or programming, well, even math is all about. We're trying to notice a pattern, and then once we notice a pattern, then we can design an algorithm, or a quote-unquote pattern generator to generate the pattern once we know what the parameters are. Okay. Yep. So now we look at this and go like, well, how do we come up with a generator for something like this? Well, I'm not going to explain how I come up with this, but that is the generator. So let's just say that we want to figure out what is K64, okay? So that means n plus 1 is 64, which means n is 63. So now we substitute n into here, and into here, and then just let this rip. We look at this and go like, but wait, we have never been introduced into these symbols. What do they mean, okay? So instead of using a sigma notation, which means summation, using addition, this is just a big OR, okay? This is a big OR, this is a big AND, this is another big AND, this is an OR. So remember, we are only talking about Boolean operations at this point. So we are basically just saying, okay, there's a whole bunch of OR, and then each component of the OR has a whole bunch of ANDs and this single term on the outside, and then there's a whole bunch of AND over here, and then the result of this huge conjunction is ended with this K0, and then this entire messy term is ORed with this kind of much smaller but still messy term. Okay, that's a generator. All right, do you guys want to see the kind of algorithmic pseudo C code equivalents of this mess? Okay, excellent. I'm just waiting for someone to say yes, because I think occasionally I get certain classes of people and go like, nah, we're good. Okay, so we look at this, and then we'll go ahead and write a, basically pseudo C code to handle this.
I don't think we can.
And let's see here. I'm looking for my mouse pad. There we go. This is from a previous class, which is no longer needed. I'm gonna put it right here. Okay. Okay, that should be good enough. All right.
I haven't won any fights.
So what we'll do is we're gonna we'll pretend that C has the bool type. I know C++ does, but C does not. Okay, so regular C does not actually have a bool type, but we'll just kind of pretend it does. And we'll call it a generator. Okay, so this is a generator function. We will have to pass a few parameters to it. So one is n. Okay, so unsigned, n is a parameter. And then we have the P, G, and K0 terms. K0 is not, it doesn't come as an array. It is just a single bool, okay, which is K0. Aiden says, doesn't it still require more time to get Kn plus 1 than Kn? That is not true. Okay, we'll get back to that one. Okay, so Aiden made a very interesting point, but I'll go back and explain that one. Once I'm done with this one, I will go back and explain why that is not the case. Okay. Okay, so remind me if I forget, okay, because I tend to forget stuff. So we have an array of G's, okay, and then we have an array of P's. There we go. So these are the parameters to the function in C or C++ that is doing kind of the same work as what we are dealing with here, okay. So what we'll do is, this is typical of how I do things. I'm going to have a local variable called result, and and I'll go ahead and return the result at the very end. And because I'm programming in C and C++ now, I have to remind myself to use semicolon at the end of each statement, because in JavaScript you do not. Okay, well, you don't need to, but you can put semicolons at the end of each line as well. So this is bool result, and because it's a huge disjunction, so that means the default value or the start value can be a 0, and then we just keep we'll just keep ORing stuff on top of this 0, okay, and that becomes the actual final result. All right, so now we have the first loop. Okay, the first loop, the outer loop is OR, and we need an index variable of I going from 0 up to n. Okay. So we need the last value of I to be actually n. Okay, we are not going to stop when I just equals to n minus 1. Okay, so we'll have a loop here. Okay, let's just stick with regular C code, because in C++ you can define a variable inside the for syntax, but in regular C you cannot. Okay, but I'm going to stick with regular C here. So we'll have an unsigned I over here, but I'm not going to initialize it up here because I will initialize it in the for loop. So we'll say for I is initialized to 0, as long as I is less than or equal to n, we'll stay in the loop, and then for each iteration we'll increment I at the end. This is the post operation. And the way I write my loops, I always open and close the braces right away, so this way I don't forget later on. Okay, so it's just tricks that help me, when I write programs. Doesn't mean that it works for everybody, but it works well for me. All right, so inside here, each term is a disjunction, is a conjunction that has gi and then a whole bunch of other terms, generated by this, nested longer end, okay, big end. So in here, I'm gonna have another local variable. We'll call this conjunctive term. Okay, so we'll call it C term, and because this is a conjunctive term, so it has to start with true to begin with, because the only thing that they can turn into is false. Okay, and it also needs a local variable j, so we have a local variable unsigned j over here. The j is needed because of this. Now, if you want to simplify this code, you can basically just say that, okay, how about we just make it g of I at this point, okay? Because g of I is, after all, the first term of this conjunctive term, so we can just say it is g of I, okay? That saves me one step, okay, when I perform the rest of the operation. So now I can focus on just this loop here, where the index variable j goes from I plus 1 to n, and each term inside is just p of I. Okay, so we'll have a j for j equals to I plus 1, j is less than or equal to n, and then plus plus j, that's the post operation. Then for each iteration, we just say, oh, okay, we are just ending the result of the overall end, which starts with the g of I, with another p of j. Okay, so now we say C term is C term and p of j, so p of j, like that. Okay, so by the time I get out of this inner loop, then I will have this entire term done. I will have the conjunctive term done. So now I can focus on the result term. So now I say result is result or C term. Okay, So this loop here, okay, the loop starting on line 3 down to line 14 is going to take care of the big OR up to and including this close parenthesis over here. So now I can look at the other one and go like, okay, let's work out the other one. So the other one, I'm going to use a local scope for this, okay? So we'll say, okay, we're dealing with another C term again. So we have bool C term, and this time we'll initialize it to case 0, because case 0 is the term that we need in the conjunction anyway, and it is not a part of the loop. So I might as well just initialize C term to case 0. Daniel says, can't we use result equals to C term? You mean up here on line 13? We cannot, because we want, because result can turn into a 1 using result or C term. But if you just say result equals to C term, that can turn it, when result is true already, you can turn it back into false, which should not be possible when you're looking at a huge disjunction of stuff. Is that making any sense? Okay, cool. So now we just have this loop here, okay? I is my index variable going from 0 to n, and then for each iteration, we're just going to end with p of I. So once again, we have for this time is I equals to 0, I is less than or equal to n, and plus I. And then with each iteration here, we are looking at C term equals to C term end P of I, like so. So by the time this loop is done, then we can go back out, because now C term is referring to this entire sub-expression, and that sub-expression is going to be ORed with result, which is already this gigantic term over here. So now we can say result is result or C term again. So yes, I know it looks exactly the same as line 13, but it is for a different term over here. On line 13, we're dealing with this kind of subterm inside the big OR, and on line 21, we are dealing with the independent, smaller conjunctive term that is outside of the big OR. So when this is all done, then we can just return result. So so is that helping? Does this help you visualize and understand how things are nested? Okay, very good. Are we still good? I'll give you guys a few seconds to think about it. Quan is asking, the second for is inside the first for loop. Well, let's not talk about first versus second, because there are actually 3 loops in this case. So how about we quote line numbers, because you guys can see the line numbers too. Okay.
It's fine.
Yeah, I'm distracting myself here. I see that 9 people are watching the lecture from YouTube. If you watch it from YouTube, you're going to have a lot of lag time. So that means, when I ask, do we have any questions, you may not have enough time to respond. Whereas, people who are watching it directly from Discord, have probably a fraction of a second of lag time, so they can respond a whole lot faster. So I encourage people to join the Discord live share instead of watching it on the YouTube side. All right, so Quan has clarified the question. The for loop starting on line 17 is not inside the for loop starting on line 5. Because if you look at the scope of this line 5 loop here, it goes from here to here. And as a result, this is a separate loop. This is a loop that is not in the bigger loop.
So treat it like little thing.
Okay, we got two more questions coming. One is from Owen, and the other one's from Kwan. Okay, so Kwan is okay with this. So if I mispronounce your name, let me know. Okay, you can always put the pronunciation of your name in parentheses as your server nickname. So that would be helpful.
I got freaking edged out. You guys are too fat.
It is not my intention to butcher, other people's name, but I'm very, very good at it.
What?
All right, so Owen is Owen? Okay, on. Okay, is asking which result are we returning on line 31 or line 21? Well, this result, okay, is continually to be updated. So this is updated one more time over here. Okay, so I can see what the problem is. Okay, we are having problem reading C code. Okay, we're having problem reading C code in a structured way. I'm not sure what I should say about it, other than after CISP310, I'm expecting people to be able to read this code and understand the structure. Now, if you suspect that I might have made a mistake, that's a different thing. Okay, but I'm expecting people to be able to read the structure of this code. Okay, very good. And Tom is saying line 21 is the last C term. It will return on line 24. Okay, so the C term in the nested block here, this particular C term, is actually not even considered the same C term as this one over here, because the scope of this C term ends when this block ends. So this C term is is an entirely different C term compared to this C term over here. But this C term is updated inside the loop on lines from line 17 to line 20, and then when this C term is done updating, it is used to update the result, because the result is looking at the result of the entire long expression. So C term, okay, C term on line 16, which is this one here, is responsible to keep track of and compute K0 and this big end of PI terms. So that's what that C term is about. But this entire thing is ORed, using this OR operator here, is ORed with whatever we got earlier, which is already stored in the local variable result. And that's why we see result equals to result OR C term, because this result is referring to this part of the expression. This C term is referring to this part of the expression. So these two have to be ORed before I return result as the final result of the function. Oh, okay, I see. Okay, I get it now. All right, so this generator is not really a generator, it's more like a calculator. So if you give me the values of K0 and all the P and all the G terms, this will calculate K of N plus 1, okay? So it's not a generator per se, it is a calculator. I could, yes, you could change the C terms to C term 1 and C term 2, but I personally like to use local blocks to control the scope of my local variables. So this way I can reuse the same name whenever it makes sense. And the reason why I call it a C term is because it's a conjunctive term, and that's what the C is coming from. But yes, in your program you can change it to C term 1 for this one, and then change all the references to C term within this scope to C term 1, and then change this to C term 2, and then once you do that, you have to change all references to C term 2 within that scope. So yes, but I personally wouldn't. It's not the way I'd like to name things, okay? But you guys are free to name things as you wish. All right. So this is not exactly a generator. So to turn this into a generator, you just have to replace the actual calculation with a string concatenation thing so that you're actually, concatenating additional operators. So instead of calculating the result, you are creating the expression to calculate the result. Okay. So why is this important? Okay, so that's the next question. Why is this important? Well, let me ask you this question. Do you think the latest AMD and Intel processors can add binary numbers? That's a pretty obvious question, right? Yes, okay, obviously they can. And the latest processors are known as, desktop processors. They are 64-bit processors, which usually implies they can natively perform binary addition in 64 bits, okay? So that means, K64 is something that you probably need to, the circuitry or the gate logic for K64 is something that, in the design process of the processor, you have to do it, okay? So instead of manually, calculating and generating that, I can use something like this, okay? In what we call an HDL. HDL stands for Hardware Description Language. So I can use control structures like this in an HDL to specify how the gates are structured. And then, that quote unquote gets compiled by what we call a silicon compiler, by an HDL compiler, which will then turn the this code, okay, this code over here, into something that we see as logic gates in Logisim, but it's not going to be represented graphically, because can you imagine how this thing would look like when we're dealing with K64? If we use individual gates, like we can use individual gates in Logisim, it's going to be super ugly. We can't track things like that anymore, right? So this is really cool because we are now generating something that is really complex, but the generating pattern itself, it's not really that complex. The result of what it's generating is complex to the point where it is not feasible for people to keep track of. But HDLs can do that, okay? A hardware description language combined with the tools can do this. And this is how we can make really complex and fast processors, because we can generalize and we can just say this is the pattern, and we can we can use the same loop here, just change this n to 128 or 127, then we can generate the carry bit of the last carry bit of a 128-bit adder, okay? But the control structure doesn't change, okay? The function itself is going to work regardless of the value of n. Okay? So I have not forgotten Aiden's question. So let's go back to Aiden's question. So Aiden's question is, doesn't this take longer to compute? The answer is theoretically no, but in practice probably yes. Okay? So what we'll do is we're going to go back to K1, K2, and K3. Okay, so we look at K1, K2, and K3. Yeah, I know you are. Yep. I'm pretty well known to be forgetful. So it is always a good idea to remind me if you need to make sure. Okay, so we look at K1 and we ask how much time does it take to compute K1. So when you look at the equation in a linear way, which is the human way of looking at the equation, then this doesn't take too much, okay? First, we need G0, which is by itself an AND operation. Then we need to look at P0, which is by itself a OR operation. And then the P0 needs to be ANDed with K0, which is an AND operation. And then after that, we have to combine the result of the first conjunction used to compute G0 with this conjunction here, which is used to calculate P0, K0. So that would be the fourth operation that we are applying in a linear sense. Okay. However, okay, it's not even that. Ripple adding is big O of n. This one is actually constant. It's big O of 1. Okay, so now if you don't understand what is the big O notation, don't worry about it. I'm not gonna refer to the big O notation, but since Aiden probably have taken already CISP430 and possibly 440. He knows what the big O notation is. So if you look at the time, the look ahead, carry look ahead mechanism in terms of time is constant. In terms of the number of gates it will use, that is a different question. That one is a little bit ugly. It's probably big O of n squared. Okay. Okay, so let's go ahead and compare K1 versus K2. I claim that if you use gate logic, it will take the same amount of time to compute K1, to compute K2, and to compute K3, and they can all happen simultaneously. In other words, I can get K1, K2, and K3 all at the same time. Okay, that's my claim. So now the question is, why? How? Right? Explain the magic. Yeah. So we'll go ahead and explain the magic. And I'm just trying to think about how to explain the magic. There we go. Okay, I know how to do it. All right. So what we'll do.
That's not okay.
Okay. So this is what we'll do. I'm going to take this out on its own. And I've just lost track of that. Okay, there we go. And then put it back here. But I want to be able to show the expressions, for K1, K2, and K3. There we go. And now I'm going to type the different phases. Okay, so we are going to separate operations in phases. All right, so this is phase 0. Okay, or I should say propagation time 0. Okay. And by the way, propagation is the word for today's row taking activity. Propagation. Propagation. So go ahead and enter that first. I'll give you guys like 20 seconds to do it. Maybe a little more. I'll give you guys until 55. You got another half minute or so. So I'll let you guys enter that first. Propagation is today's word for row taking purposes.
Popping that singular potion would make a difference. They don't have any global alts, right? There we go. I don't know. Should I stick and try and peel the scion off, or should I go and harass these steps?
It's nice to have a clock on the recorder. Okay, so it is 55. If you don't have enough time to do it, just kind of write it down on the side, so this way you don't forget to participate in that activity. Okay, so in propagation time 0, okay, we're going to compute all the p and all the g terms. Okay, so we can now compute all p and g terms all at the same time. They can all be done in parallel because there's no dependency between the p and the g terms. P1 only depends on x1, y1, right? P0 only depends on x0, y0. So there's no reason why we cannot use different OR gates to compute P1 and P0 at the same time. And that applies to all the g terms as well. So in one single slice of time, so to speak, okay, in one propagation time period, we can now compute all the p and all the g terms, and they're all ready at the same time. Okay, so we got some questions coming. There is voice in the background that is talking. That's my son, actually. Is it loud enough for you guys to hear?
I keep thinking that Ash cooldowns on the long, like Ash goes on the long for them.
A little bit. Okay, let me see if I can turn down the my mic volume just a little bit so that you guys cannot hear that. Okay. Well, I'll give it a try. And let's see, we're getting to here. All right, so we are looking at the recorder input device, change my mic. I'll turn it down by maybe 3 decibel. Okay. 3 decibel is 1/2 of something, approximately. Okay, there we go.
Oh.
All right. So can you guys still hear me okay? All right. Yes. Closed captioning is going to be there, but it won't be there instantaneously, so it takes a little bit of time. All right, so getting back to the text here. So I am just going to write down here that we are computing all the P and all the G terms in propagational time 0. So once we have that, okay, then we can compute P0, K0, we can compute P1, G0, we can compute P1, P0, K0, we can compute P2, G2, we can compute all of those at the same time. So that means in propagation time 1, okay, propagation time 1, we'll now compute all the conjunctive terms, okay, so compute all conjunctive terms at the same time, okay. So now if you look at this conjunctive term, it only has got 2 items in it. This one has got 3 items in it. This one has got 4 items in it, but they only take the same amount of time. The gate itself is more complex because we are talking about a 2-input AND gate here. We are talking about a 3-input AND gate here, and we are talking about a 4-input AND gate here. But the amount of time it takes to finish the computation is the same, okay? So that means, you know, all of these conjunctive terms can all be done at exactly the same time, in theory at least. So I'll go back and talk about why it is only in theory, you know, why in the physical world, you know, that usually cannot be the case. How is a 3 AND done using this? How does it get done in the same amount of time as a 2 AND? Okay, so remember the NAND gate that we looked at? Can anyone kind of think of, you know, a NAND 3 gate? Instead of 2 NAND, it's a 3 NAND. It's because, you know, it just has more transistors. Aiden, a 3-input AND gate has more transistors, so it is structured. So in terms of the structure, it is a little bit more complex, but the amount of time it takes for the result to pop up, you know, to come out from the input is still the same.
I would not recommend going.
Nope, that's not what we're doing. That's why, you know, most people think about, you know, these operations and think that, you know, this operation, which is a 3-term AND, is going to take more time than the 2-term AND. But in hardware, because we can have multiple input AND gates, and in theory, they take the same amount of time regardless of the number of inputs. It is just that the circuitry is more complex, but it doesn't change the amount of time. Yep, okay, very good. So now we look at propagation time 2. Okay, so let's go back to here. So when we look at propagation time 2, which you cannot see yet, because I haven't hit the escape key, then we can compute, you know, finish all the K terms, because by the end of propagation time 1, we would have all the conjunctive terms done already. So using the third propagation time 2, we are now just, you know, combining all of the conjunctive terms using a disjunction. Now, are those big disjunctions? Some of those are really big, because, you know, K1 only has a 2-input disjunction, K2 has a 3-input disjunction, and then K3 has a 4-input disjunction. But as I said a little bit earlier, we can design logic gates that have multiple inputs, but it is still just performing a OR, and it takes the same amount of time regardless of how many inputs is to that gate. So getting back to this one here, so that means, you know, we can simultaneously get all the K terms done. So after all the K terms are done, okay, then we can now compute. What about the Q terms? Okay, when do you think we compute all the Q terms? So the Q terms can be computed in propagation time 0. Okay, so in addition to computing all the P and then all the G terms, we can also compute all the Q terms, because after all, the Q terms are exclusive ORs between the X and the Y, right? So there's no reason why we cannot have those, happening at the same time when we compute the conjunction and the disjunction of the X and Y terms. So P, G, and Q can all be computed simultaneously at the same time at propagation time 0. And then propagation time 1, we need to compute all the conjunctive terms, inside each one of the K disjunctive term. And then in propagation time 2, we finish all the K terms. And once we have all the K terms, we can now have exclusive OR. So we can now, this is propagation time 3. So in propagation time 3, we can now finally have all the K terms, and all the Q terms are ready here as well. So now we can finish all the S terms, okay? So now we got the sum, right? So in 4, okay, let me get back to here. So in 4 propagational delay time, okay, assuming the propagational delays are about the same, okay? So in 4 propagational delay time, we will have the result of the entire sum, all the bits, all at the same time. And none of this, okay? How long does it take for propagation time 0 to finish? How long does it take for propagation time 1, 2, or 3 to finish? None of these depend on the number of bits. So whether you have a 8-bit adder, a 64-bit adder, or 128-bit adder, it will still take only 4 propagational delay time to get it done. So let me finish the typo here. Propagation. There we go. Okay. So are we now starting to understand why carry look ahead is great? Because in theory, okay, we only need 4 propagational delays to compute the sum, and that's regardless of how many bits we are trying to add. Isn't that cool?
So fast.
Yeah. So you can kind of also imagine, now most of the textbooks, in this type of discussion will only talk about carry ripple adding, okay? Because carry ripple adding is very simple to explain, and it is correct. It gets the result, but it is really slow, okay? You can just kind of imagine between AMD and Intel, if one of them uses carry ripple adder and the other one says, well, I know carry look ahead adder are more complex, but we're going to go for that, okay? Because we can fit more transistors onto the die now. You can immediately see which one is going to lose market share big time, because whichever company sticks with carry ripple adding is going to have I mean, the process is going to perform like a dog. I mean, it's going to be a very slow processor. All right. So are we good so far? There's a lot of material, a lot of concepts to grasp in this discussion. So we do have a long weekend, right? I mean, we have a 5-day weekend until the next time we meet. So that means, you probably want to spend time to review the material. And when I say review the material, it's not really just reading the material, but you kind of have to focus on understanding how all the pieces connect in this. Look at the detail, look at the pine needle, but also spend some time to look at the pine forest, because you got to look at the bigger picture, how these things interconnect. All right, so now that this piece is done, we got a few options. Oh, okay, in 15 minutes, okay? I got about 15 minutes left, a little less than that. Let's go ahead and implement the slow adder, okay? Let's go ahead and implement the carry ripple adder. So to implement the carry ripple adder, we just need to kind of go back to some of the equations here, because we need to be able to compute the carry bits, the K bits, the Q bits, and so on and so forth, okay? So we'll go back to this portion of the discussion. And then we'll go ahead and I'm just looking at the side because my mirror setup is actually blocking my view. And I'm going to type in the command to get into LogicSim. Oops.
Cho'Gath is the only person that could
There we go.
that entire game.
All right, so here's LogicSim. So the first thing we want to do is to create what we call a half adder. Okay, so we go to Project, Add Circuit, and I'm just going to use HA, to abbreviate my half adder. So the half adder is going to have two outputs. One output is the R, the output is the C, is the carry. Okay. So the input, I'm not sure whether I should label those X and Y because X, Y have special meanings. So let's not use X, Y for those. We'll just call it A and B. Okay. So the first input is input A. The second input is input B. Oops, B, not B. Like so. I'm just looking at the letters. I think I can still use B in this case because we haven't gotten to the binary subtractor yet where B is borrow. So we're still good at this point. So we'll go ahead and create an output. So the first output is the result, the single digit result of adding A and B. And then the second output is going to be the carry of adding A and B. Okay, so I'm just labeling all the pins first so that it is clear what we want to do in between. So now we look at AB and we ask, how do we get to the result, the single digit result of adding A and B? We'll just go ahead and use exclusive OR, okay? Because I could have done it using one level of AND and then one level of OR, but just for the purpose of illustration, we'll just go ahead and cheat and use an exclusive OR gate. So we pull this exclusive OR gate. We change the number of inputs to 2 because we don't want to leave any input pins unused. Okay, that's one big, huge no-no in any type of hardware design. So here's our exclusive OR gate, and it is used to compute the result. Okay, so A goes into the first input pin. It doesn't matter which one is which one because exclusive OR is commutative, which means which one you specify as the first pin, which one you specify as the second pin, doesn't really matter. The carry is done using a conjunction, so we just pull a AND gate out, okay? And we do the same thing, change the number of inputs to 2, and then we change the size, so we use the smaller representation. It's just that it looks nicer, looking like this. And then we make all the connections like that. There we go. And then the output of the exclusive OR becomes the single digit result, and then the output of the AND becomes the carry. So this is what we call a half adder. So now what we do is we turn it into a chip. Okay, so by changing the view to the appearance view, this is turning into a chip, which is kind of the same thing as looking at the prototype of a function instead of the definition of a function. So it helps to kind of know which one is which one. So we'll just label A, B. This is the result, the R, and this is the carry of those 2 bits. Okay. So after this, we can rearrange the ABCR.
Yeah, I haven't played Blitzbang.
So this way it doesn't use up a lot of space outside of the chip.
Oh my god.
Okay. And we'll even label the chip itself, as a half adder. So we'll just say, HA on the outside. Okay. It's really not necessary, but it does make things a little bit more clear. Okay. So now we have a component. I have just created a component that I can use in the second level component. So if I have one component called a half adder, what do you think is the other one? The other half, the better half. Okay, we'll call it the full adder, okay? I don't understand how we can have a third if we have one half, the second half. What about the third one? All right, so this is the full adder, okay? And I'll ask, I know you guys know the answer already, but I'm gonna ask anyway. How many half adders do we need to make a full adder? I know Aiden's gonna say 3. Okay. Yes, 2. All right. So we'll slap 2 half adders into the screen, and then we say, okay, now how do we combine these things? And how does it correspond to, just doing the addition by hand? So one full adder is basically one column, of the manual adding process. Okay. So now we got to label the pins very carefully. So we have one pin called X, which is 1 bit from the number X. Another input pin called Y, which is, in fact, I'm going to use X bracket something. Okay, so we'll say X, this is bit I of X. This is bit Y of Y, and it'll be clear why I need to label the index, okay? Because one of the input is a carry bit from the previous column. So we need, we need another input pin here, and it is the K bit, but it's not KI. This is the input, which is KI minus 1, okay? The reason why it's KI minus 1 is because in order for a column to finish its own calculation in addition, we also need to know what is the carry coming in from the previous column. And the previous column is column I minus 1. And I'm gonna arrange things a little bit differently like this, and later on it'll be clear why I want to arrange it that way. Okay. So now we look at the definition of Q. Okay, Q is R of X and Y, right? So we'll take the first half adder, and then we'll just say, okay, we'll connect X to A, we'll connect Y to B, and whatever is coming out of R is our Q bit. Okay, we call it Q. Okay, so even though it doesn't have its own pin to connect to, because it's an intermediate result of the column. It doesn't have a pin because it's not an actual output. So it doesn't really have a pin to connect to. So I can only use this method to give it a label, and we'll call this Q of I. Okay, so this wire is actually Q of I. So the other adder, okay, is going to take Q of I, but it's going to combine Q of I with K of I minus 1. So K of I minus 1 is the other wire coming into the second half adder. Okay, so when you look at the result of Q and K, what do we get? Actually, I take it back. This is actually just K of I. It's not K of I minus 1. This is actually K of I. It's the output that I have to change to Ki plus 1. So I stand corrected. This is actually just K of I. So K, between the K and the Q bits, okay, if you apply the R function to K and Q, we get the sum bit, right? The sum bit itself is really useful, so it has its own output pin. So this is S of I as an output. Okay. So are we doing okay so far with corresponding components in this particular circuitry to how we perform multi-digit addition? Are we still doing okay, or are we partially lost? All of these are really just based on the equations and all the definitions that we have done up to this point. And some of those, or most of those, were done on Tuesday. Like the definition of Q. Okay. All right. Okay. So we'll wait until how. Okay. So now we got the 2 carry bits here. This is C of Xi, Yi. This is C of Qi Ki. Okay.
Shit,
So
I
now
missed
we
the minute.
ask,
I was
what do we
walking.
do with those two C bits? Okay. So let's go back to this to the slide over here, and we can see that Ki plus 1 is C of Xi Yi or C of Qi Ki. Oh, okay. So now we can go back here and say, okay, this is C of Xi Yi. This one over here is C of Qi Ki. But each one is not enough to finish the circuitry because they need to be ORed to become K of I plus 1. So now we pull an OR gate, and then we do the same thing. Okay, change the number of input pins to 2, and then change its shape so it's a little bit smaller. Okay,
Yes.
so we take this OR gate, and then we say, let's go ahead and do an OR between the C or the carry between Qi Ki, and we'll also take the C, the carry of Xi Yi into this OR gate. The output of this OR gate now is going to an output pin because it is actually useful, because it is actually what we will call as our K of I plus 1. All right, so there's a point Daniel is asking, can you or them without the gate just by connecting the two wires? No. So between this wire and this wire here, they cannot just be connected because they're two output pins. When you connect two output pins, if the two output pins are actually different, you end up with a fight between the components because one component wants to drive the wire to a higher voltage, and the other output wants to drive the output to a lower voltage, and they're just going to fight, and some transistor will burn out in the process. So you cannot just connect them together. You need an OR gate to basically say the output is a 1 if and only if at least one input is a 1. Okay. All right. So this is a full adder. So now that we have a full adder, we'll use the mains. Oh, let's change to the appearance. Okay, it has got 3 pins. So with the 3 pins, we'll do some labeling. Okay, one is K in. Okay, is the input carry. One is X. One is Y. And then as far as the output is concerned, one is the sum bit, and the other one is the K out, okay, carry out. And we'll move these things around a little bit so that it looks a little bit nicer. Okay, so K in is here, Y goes here, X goes here, S can go here, and then K out, I'll just let it sit outside because it takes up a little more space. All right, so now we go to main, okay, and we want to create, let's say, a 3-bit by 3-bit adder, okay. So with a 3-bit adder, we're going to specify 3 input pins, a 3-bit input pin. So we do it by changing the data bits to 3. So now we have a 3-bit input pin. We'll call this X. And then we'll duplicate it so it becomes Y, because Y and X are kind of structurally the same, they're just labeled differently. So here's our Y, and then we have a 3-bit output pin, which is our sum. So the sum always has the same number of bits as the input, and then we have a K in and K out, but this time we can label these actually technically as K0 as an input pin. Oh, this is an output pin, so we'll stash it over here. It is K3, and then one of the input pin is K1. Oh, K0, sorry. K0 is our input pin over here. All right, so now we know that there are 3 columns. If we are to do this calculation by hand, there will be 3 columns. Each full adder is representing 1 column when we perform the addition manually. So now we go to FA, and then we basically get 3 of them. Okay, 1, 2, and 3.
Let's get them.
Okay, and we'll kind of stack them up in a nice way, like so. There we go, and there we go. All right, So one thing we notice is there's a K in and there's a K out. So it only seems logical, right, that we connect all the K outs to the K ins. Okay, so we hook it up like this. And then we hook up this one similarly to over here, like so. And then the final K out is our overall carry bit, which is K3. So we hook it up like that, okay? So that's the easy part. And then K0 is the only input pin that is labeled as a K as a carry. So it goes into K in of the least significant bit full adder. So now we have X and Y. Now, if you try to connect this to here, it's going to be a problem because this is a 3-bit pin, and this is a 1-bit pin. So that's why it will complain and say that we have incompatible width. So this cannot happen. Well, we just need one thing in between to make this happen. Can anyone remember what you did with one of the labs to basically break all the individual components out? It's called a splitter. Very good. So we go to wiring, and then we pull out just one splitter. We'll just make copies of that. So we take out one splitter. But we have to remember that we are dealing with 3 bits here. So the bit width is going to be 3, and we need all 3. So we want the fan out to be 3 as well. So it will automatically number the bits to bit 0, bit 1, and bit 2, which is what we need. So there's no need to change any of that. But remember what I said, we need 3 of these. Okay, so we'll make copies of these so I don't have to individually reconfigure the bit width and also the fan out. So now we just have to reposition X a little bit so that I got some room for the split bits to go places. So bit 0 go to this X, bit 1 goes to this X over here, and then bit 2 goes to this X over here. And then we look at Y and we go like, okay, we have to split Y the same way that we split X. So now we connect another splitter to Y, like so. And then X0 is going to the same adder. So now I have to be really careful of how I draw the wires because I don't want any unintended connections. So bit 1 goes to this one, and then bit 2 goes to this particular one. So we're almost done, right? Because we have an output pin that is 3 bits wide, but each one of the full adder only gives us a single bit sum. So we need to turn the splitter into a merger. How do we turn a splitter into a merger? This is so difficult because the word splitter, I cannot change a splitter. There's nowhere in here to say, let's turn the splitter into a merger. What are we going to do? Okay, I can see the class is a little bit tired at this point. Yes, we just changed the facing. There we go. Now we have a merger. All right, so now we got a merger. We just have to give it the right bits to merge, okay? This is bit 0. It goes here. This is bit 1. It goes here. And this is bit 2. And it goes here. There we go. Here is our 3-bit carry ripple adder. Okay? Change the direction. Yeah, we can pretend, but it will look awful, right? So it's nice to kind of switch the facing direction so everything goes from left to right, just like how most of us read from left to right, because I know there are languages where it reads right to left. Okay, wow. Through advanced binary logic, we have figured out that 0 plus 0 is 0. But wait, there's more. Aiden, but there's more. We can perform multi-digit addition. So turn your tool into the what we call the poking tool. So now we can say, what about 5 plus 1? Okay, 5 is 1, 0, 1. and then 1 is just 0, 0, 1. And we can tell that, hey, the result of 5 plus 1 is 6, because 1, 1, 0 is 4 plus 2 plus 0, so it is 6. Woohoo! Okay. No. So Daniel, we do not count we don't count K3 as a part of the sum. The sum and x and y, they all have to be the same width. So the extra carry bit, we just call it the carry out of the entire adder. In this specific case, we can call it K3 because we know we're dealing with only 3 bits. So that means if I add 3 to 5, then I should set the overall carry. Okay? Can I slow down Logisim so we can see a ripple? No, unfortunately we cannot. I have already looked into it, and I don't think Logisim can simulate propagational delay. Even though it understands some of the concepts of propagational delay, it doesn't quite emulate the propagational delay.
Unless die.
I don't think that's going to help. Okay, but there's one clue that we have that linear dependency, because we can see how K3, in order for K3 to compute correctly, it needs all of its pins to have the right input, right? But we can see one of the inputs is the output of the second full adder. But we know also, in order for this full adder to work, it needs to have all 3 of its inputs being the correct input. But that means this K in needs to come from the first full adder. So that means until the first full adder is done, the second full adder cannot give us the correct K output. Until the second full adder is done, the third full adder cannot have the correct K output. So that is why it's called carry ripple, because if we change any of the inputs, it can be K excuse me, can be K0, can be the bits in X and Y. The changes need to happen. It first has to change the first full adder, then we'll change the second full adder, and then we'll change the third adder. And there's a linear dependency on those things. And this is why it is called carry ripple adder. And unfortunately, we cannot, this has nothing to do with the hertz of a CPU, Aiden, because the clock speed has to do with synchronous operation. And what we are looking at here is what we call an asynchronous circuit. An asynchronous circuit does not need a clock. Changes happen basically as soon as, as soon as one of the inputs of a gate is changed, the gate will start to change its output. It does not need to rely on a clock. So just being nitpicky here, okay, Aiden. So it has nothing to do with the clock speed. It has to do with propagational delay, and there's no setting in Logisim to slow down the propagational delay. You can have a processor using 7 nanometer transistors and still clock at 2 hertz. That is a good question, Aiden. I have not yet looked into that portion of the code in Logisim to see whether it really simulates the gate with propagational delay also simulated, or whether it is using a software trick just to figure out the dependency and not really use propagational delays. I believe it does not really use propagational delays. All right, well, it is 8:31. You get another 11 minutes of free lecture time. Woohoo! And there's a lab for today. Okay, so there's activity for you guys to do. Let me go back to the notes. Okay, where is it? There we go. Well, I mentioned the row passcode already. Christian.
Yeah. Okay.
That was the whole point. I want you guys to be. It starts with a P and I forget the word. It's propagation, okay? It's propagation, but don't type it up in the text channel. I'm gonna write a bot. It will erase every single text message that mentions that word. It is propagation, okay? But you need another passcode, okay? Because the lab has its own passcode. So the lab that you guys are gonna do today is multi-bit stuff, okay? Which has some of the things that I just did, okay? Using the multi-bit input pin and output pin. But you guys are gonna do multi-bit gates as well, okay? So this is a really kind of interesting lab to prepare you to implement carry, look ahead, adder, and subtractor later on. But it's a very important step to understand what is a multi-bit gate and how it works, okay? So that's one thing that you need to know. The passcode of the lab is multi, M-U-L-T-I, and I will just write it down in the text channel. The passcode of the lab is multi. Okay, so I got a few people typing, and we will. All right, you're welcome. Okay, cool. So now you guys got 3 things to do over the long weekend. Okay, personally, I prefer Monday, Wednesday, Friday classes, but the majority of the class wants Tuesday, Thursday, because I don't like really long weekends. Okay, but over the long weekend, you guys got 3 things to do right away. Okay, if you have not done it already, go to the row-taking activity for today and use the word propagation, okay? And if you don't know how to spell propagation, make sure that you look it up first, because this is a one-shot thing. If you're typing the wrong word, it won't let you try again. So that's one. The second thing is the row window has always been the same. It is 24 hours since the beginning of the synchronous lecture. So that has not changed from the beginning of the semester, because I think I told you guys in one of the announcements, and that has not changed. Second thing, okay, work on the lab. Now this lab, if you just work on it, it won't take you too much time. You can probably get it done tonight in maybe 45 minutes or so, okay? So I would just kind of do it right away instead of wait until next Monday to do it. Okay, so that's the second thing. The third thing is to read ahead of me, okay? Now, don't read ahead of me unless you have reviewed the material that we have gone over up to this point and you fully understand the concepts, okay? But once you have done that, okay, I want you guys to read ahead of me and read the binary number subtraction module. If you fully understand how we are doing binary addition, especially how we are using the carry look ahead mechanism, and how the carry look ahead equations work out, how the expressions work out, binary number subtraction is going to be super easy for you, okay? Once you understand the concept, it's really kind of the same concept, except we are going to apply that to subtraction. So you might think, but addition and subtraction are very different, because one is commutative and the other one is not commutative. They're two really kind of different concepts. That is true in base 10. But in base 2, as you will see in the binary subtraction module, the difference between adding and subtracting is very, very small, okay? So when you get to it, you will see it, okay? But don't go to read the subtraction until you have the addition down, okay? And I mean, fully understanding the concepts. You don't need to fully understand the Boolean algebra derivation stuff, but you do need to understand how we expand equations or expressions in one and another to get to the result that we want. And you also need to understand why carry look ahead is so much better compared to carry ripple. All right. So with that, I am going to stop the live stream unless I see additional questions. Okay, I don't see any additional questions. So I'm gonna stop the live stream, and have a nice weekend, everybody, if I don't get to talk to you in the lab time. So I'm gonna go away for about 10 seconds. I cannot eat my dinner in 10 seconds. So I'm gonna go away for 10 minutes and then come back to the text channel to answer questions if you guys want to go ahead and get started with the lab, or if you want to ask any questions related to today's lecture. All right, so here we are. I'm gonna